Alaikum. Today we want to continue talking about chapter 1, section 1.5, uncertainty in measurements. Two kinds of numbers are encountered in scientific work: exact numbers, those whose values are known exactly. Example, 12. There are 12 eggs in a dozen. 1 kilogram contains 1000 gram. Exact numbers can also result from counting objects, as if you say there are 20 men in this room. Inexact numbers, those whose values have some uncertainty. Example, all numbers obtained by measurement are always inexact. Remember, uncertainties always exist in measured quantities. Now, precision and accuracy. Now, the terms precision and accuracy are often used in discussing the uncertainties of measured values. For example, precision refers to the proximity of several measurements to each other, whereas accuracy refers to the proximity of a measurement to the true value of a quantity. Now, this dart analogy illustrates the difference between these two concepts. Here in the above one, here you have all the darts in the middle, so we have good accuracy, good precision. Here the darts are close to each other, but they are out of the center, so we have poor accuracy but good precision. And here we have scrambled darts, so we have poor accuracy and poor precision. Now, in the laboratory, we often perform several trials of an experiment and average the results. Now, the precision of the measurements is often expressed in terms of the standard deviation. So, the smaller the standard deviation, the better are your results. Also, this figure reminds us, however, that precise measurements can be inaccurate, as you can see here. For example, if a very sensitive balance is poorly calibrated, the masses we measure will be consistently either high or low. They will be inaccurate even though they are precise. Now we want to talk about significant figures. Suppose you determine the mass of a dime on a balance capable of measuring to the nearest 0.0001 gram. You could report the mass as 2.2405 plus or minus 0.0001 gram. Now, the plus or minus notation expresses the magnitude of the uncertainty of your measurements. Now, significant figures refers to all digits of a measured quantity, including the uncertain one. The greater the number of significant figures, the greater the certainty implied for the measurement. When rounding calculated numbers, we pay attention to significant figures so we do not overstate the accuracy of our results. Now, to determine the number of significant figures in a reported measurement, read the number from left to right, counting the digits starting with the first digit that is not zero. In any measurement that is properly reported, all non-zero digits are significant, because zeros can be used either as part of the measured value or merely to locate the decimal point. They may or may not be significant. So, here are some rules. All non-zero digits are significant. Zeros between two significant figures are themselves significant. Zeros at the beginning of a number are never significant. Zeros at the end of a number are significant if a decimal point is written in the number. Now, a problem arises when a number ends with zeros but contains no decimal point. Now, in each case, it is normally assumed that the zeros are not significant. And to explain this, exponential notations can be used to indicate whether end zeros are significant or not. So you convert your number with zeros into an exponential notation, and depending on where you put the dot, then you have your number of significant figures. Significant figures in calculations. Now, when carrying measured quantities through calculations, the least certain measurement limits the certainty of the calculated quantity and thereby determines the number of significant figures in the final answer. Now, the final answer should be reported with only one uncertain digit. Now, to keep track of significant figures in calculations, we will make the frequent use of two rules, one for addition and subtraction, and the other for multiplication and division. So we start with addition and subtraction. When addition or subtraction is performed, answers are rounded to the least significant decimal place. Suppose in this example you want to add these three numbers. Notice that this number has 2 decimal places, this number has 3 decimal places, and this number has only 1 decimal place. So after you add all of them, you get this number which contains 3 decimal places. So your answer should contain only 1 decimal place. So you count here 1, and then 4 is less than 5, omit, and then you get this answer. Now, when multiplication or division is performed, answers are rounded to the number of digits that corresponds to the least number of significant figures in any of the numbers used in the calculation. For example, if you want to find the area of a room with these of a box with these dimensions, 2.221 centimeter length and 5.2 centimeter width, and you want to find the area, and here we must look at the number of significant figures. Here all these are non-zero digits are significant, 1, 2, 3, 4. Here we have 4 significant figures. Here we have 1, 2 significant figures, and this is the answer. So which one has the least number of significant figures? This one. It has 2 significant figures. So our final answer must be reported with 2 significant figures. So we count 1, 2, and then 3 less than 5, omit, and then you get your final answer, 32 square centimeter, because 5.2 has 2 significant figures. Notice that for addition and subtraction, decimal places are counted in determining how many digits to report in an answer, whereas for multiplication and division, significant figures are counted in determining how many digits to report. Now, in determining the final answer for a calculated quantity, exact numbers are assumed to have an infinite number of significant figures. If we say there are 12 inches in 1 foot, the number 12 is exact, and we need not worry about the number of significant figures in it, because it has an infinite number of significant figures. Now, in rounding of numbers, look at the leftmost digit to be removed. Now, if the leftmost digit removed is less than 5, then the preceding number is left unchanged. and if the leftmost digit removed is 5 or greater, the preceding number is increased by 1. Now we come to when a calculation involves 2 or more steps and you write answers for intermediate steps, retain at least one non-significant digit for the intermediate answers. This procedure, of course, ensures that small errors from rounding at each step do not combine to affect the final result. Now, when using a calculator, you may enter the numbers one after another, rounding only the final answer. Remember, accumulated rounding of errors may account for small differences among results you obtain and answers given in the text for numerical problems. Now we come to last topic in this chapter, section 1.6, dimensional analysis. Now, throughout the text, we use dimensional analysis in solving problems. So in this chapter, units are multiplied together, divided into each other, or cancelled. Now, the key to using dimensional analysis is the correct use of conversion factors to change one unit into another. Now, what is a conversion factor? Is a fraction whose numerator and denominator are the same quantity expressed in different units. We use dimensional analysis to convert one quantity to another. Most commonly, dimensional analysis utilizes conversion factors. Example, 1 inch equal 2.54 centimeter. So remember, this relationship allows us to write two conversion factors, that there are 2.54 centimeter per inch, or the 1 inch equal 2.54 centimeters. So this is a conversion factor, and this is another conversion factor. You can use either one depending on the problem you are working with. So we use, for example, this conversion factor to convert inches to centimeter, and the other one for the opposite process. In general, we begin any conversion by examining the units of a given data and the units we desire. We then ask ourselves what conversion factors we have available to take us from the units of a given quantity to those of the desired one. As we see here, so use the form of the conversion factor that puts the sought for unit in the numerator. So here, when we multiply a quantity by a conversion factor, the units multiply and divide as follows. This is the given unit that you want to convert into the desired unit. So you multiply this by a conversion factor which consists of desired unit divided by given unit. This is the conversion factor. So you see here we cancel given unit with given unit, and then we get the desired unit. So in the desired, if the desired units are not obtained in a calculation, an error must have been made somewhere. So careful inspection of units often reveals the source of error. Now, using two or more conversion factors. Now, it is often necessary to use several conversion factors in solving a problem. As an example, let's convert the length of 8 meters rod to inches. Now you see here the 1 inch equal 2.54 centimeter, and also from SI prefixes we know that 1 centimeter is equal 10 to the minus 2 meter. Thus we can convert step by step, first from meters to centimeters. As you can see here, we can convert from meter to centimeter here, and then from centimeter to inches. So we have here two conversion factors. We use them here down. So you have 8 meter and you want to convert it to inches. First, we use the first conversion factor here. 8 times 100. There are 100 centimeter per meter. So you see here, this meter cancels with this meter. And then we use the second conversion factor. 1 inch contains 2.54 centimeter. So here centimeter goes with centimeter, and here your desired unit is here. So we have here the answer is 315 inch. Now the first conversion factor is used to cancel meters, as we can see, and convert the length to centimeter. Thus meters are written in the denominator and centimeters in the numerator. Now the second conversion factor is used to cancel centimeters here and convert the length to inches. So it has centimeters in the denominator and inches, the desired unit, in the numerator, as you can see here. Note that you could have used 100 centimeter equal 1 meter as a conversion factor as well in the second parenthesis. As long as you follow your units and cancel them properly to obtain the desired units, you are likely to be successful in your calculations. Now, conversions involving volumes. Now, the conversion factors previously noted convert from one unit of a given measure to another unit of the same measure, such as from length to length. Now, we also have conversion factors that convert from one measure to a different one. For example, the density of a substance can be treated as a conversion factor between mass and volume, as you can see here. Now suppose we want to know the mass in grams of 2 cubic inches, here 2 cubic inches of gold, which has a density of 19.3 gram per cubic centimeter. Now the procedure is diagrammed on the next slide, as I will show you. The final answer is 633 gram, reported to 3 significant figures, the same number of significant figures as in 2.00 and 19.3. This one has 1, 2, 3 significant figures, and this also has 1, 2, 3 significant figures, and the answer is 633, which also has 3 significant figures. So if we look at this figure, it shows us the procedure. The given inches, use this conversion factor, the first one, to convert cubic inches to cubic centimeter, and then use this second conversion factor, which is the density. You remember we said the units of the density, gram per cubic centimeter. Use this to get the final or the desired unit, that is in a gram. So the final answer, as I said, is 633 gram, which consists of 3 significant figures, the same as this and the same as this. Okay, let's look at some examples here. Converting volume units. Earth's ocean contains approximately 1.36 times 10 to the 9 cubic kilometer of water. Calculate the volume in liters. So this is the solution. So this problem involves conversion of cubic kilometer to liter. From the back inside cover of the text, we find in 1 liter equal 10 to the minus 3 cubic meter, but there is no relationship listed involving cubic kilometer. So from our knowledge of metric prefixes, however, we have in 1 kilometer equal 10 to the 3 meter, and we can use this relationship between lengths to write the desired conversion factor between volumes, which is this. Okay. Then 1000 meter per 1 kilometer, cube them, and you get this 10 to the 9 cubic meter for each 1 cubic kilometer. Thus, converting from cubic kilometer to cubic meter to liter, we have this one. You see here, units cancels out. Units cancels out, and liter is our desired unit. And the number of significant figure here is 1, 2, 3. It is the same as our given unit, 1.36. Okay. Now in this practice exercise, you can solve it by yourself, and here you have the answer. Another example, convergence involving density. What is the mass in grams of 1 gallon of water? The density of water is 1 gram per mil. We are given 1 gallon of water. The known or given quantity are to calculate the mass in grams. We have the following conversion factors, either given, commonly known, or available. 1 gram of water, 1 mil of water, 1 liter, 1000 mil, 1 liter al quart, 1 gallon per quart. Now the first of these conversion factors must be used as written with the grams. So you must use, you see, all these conversion factors, 1, 2, 3, and 4, to get your final answer in a gram. So the mass in grams is 3.78 times 10 to the 3 gram water, and the answer is reported to in 3 significant figures, 1, 2, 3, the same as here, 1.003 significant figure. Now the units of our final answer are appropriate, and we have also taken care of our significant figures. We can further check our calculation by the estimation procedure. We can round this off to 1, focusing on the numbers that do not equal 1, then gives merely 4 times 1000 for 1000 grams, in agreement with the detailed calculation. So here a continuation of the solution of the previous problem. You can read it by yourself, and then you can practice this exercise, which is somehow similar to the sample exercise. Okay, this is the end of chapter, or part 2 of chapter 1.